The International Geophysical Year 1957-58 has been described as the most significant peaceful activity since the Renaissance and the Copernican Revolution. It marked the dawn of satellite technology and the observation of Earth from space, global plate tectonics, the setting aside of the whole continent of Antarctica as a scientific reserve, and many other milestone events. It was an amazing achievement of international scientific diplomacy to launch such an effort against the background of the Cold War and to rally 66 countries, including the Soviet Union, to participate. Station Alpha was the first long-term scientific base on Arctic pack ice operated by a Western country. At the time of its establishment, the Soviets had already operated 6 drifting stations of that kind, but owing to the particular strategic importance and sensitivity of the Arctic basin, little information from these Soviet stations had reached the West. It was the variety and vigor of the numerous projects conducted at Station Alpha that went a long way toward catching up with our Russian colleagues. Some of the reports published from this work have become an established and often quoted part of the scientific literature, most notably in physical and biological oceanography, sea ice physics, and air-sea interaction. If there had been any satellites in the spring of 1957, they would have seen an Arctic sea ice cover that looked like the white area in this map. This ice floats on the ocean, covering about 10 million square kilometers, and it is anywhere between a few centimeters and several meters thick. Winds and ocean currents push and stretch and shear the ice around, breaking it into a chaotic array of pieces of different size, separated by pressure ridges and sometimes by wakes of open water. After many reconnaissance flights by the US Air Force, a cluster of thick old ice floes was finally located in March 1957, more than 1,000 kilometers north of Point Barrow, Alaska. The green dot in the map marks the point where our drifting station was established. From there, it drifted for 18 months along a meandering and looping path covering a distance of over 3,000 kilometers to the location marked by a red dot where the project ended in November 1958. In April 1957, a ski-equipped C-47 landed on the ice and deployed the first team of workers. They included an Air Force major as camp commander and several soldiers with technical skills who had volunteered for 6 months duty on the ice, plus 4 of the typical tough and versatile Alaskan construction workers. Modular buildings called Jamesway huts, camp supplies, fuels, 2 small World War II Studebaker tractors called Weasel, and a small bulldozer were dropped by parachutes. It is of course always nice when the necessities of life fall out of the sky, but in our case they came scattered all over the so-called countryside, and collecting them was hard work. We learned very quickly that all the supplies and equipment had to be stacked and stored in systematic order. In spring, the snow is still cold and dry, and the almost perpetual slight snowdrift can bury essential pieces of equipment that won't be found until July, when all the snow will be melted. By mid-May, this amazing first crew of workers had built living huts, a mess hall, a laboratory, and the camp was ready for occupancy by the rest of the scientists. The next order of business was to clear the snow away from what was to be the runway. At that time, we had no access to heavy cargo planes on skis, so the runway had to have a hard surface for aircraft on wheels. The finishing touch of such a runway is achieved by dragging a heavy wooden frame behind a tractor to smooth out the last snowdrifts. It may seem somewhat foolish to do all this work on a sheet of ice that is only 2 to 3 meters thick and may split apart any day and form pressure ridges that can grind down and destroy everything. But we were lucky. This first piece of ice in our camp and all the installations held together for a whole year. As you can see on this first landing, this C-124 Globemaster heavy cargo plane came precariously close to breaking the nose gear because there was a long, gentle bulge in the ice that we were unable to level out. Our camp had 10 Jamesway huts, the smaller ones with a 5 by 5 meter floor and the larger ones 5 by 10 meters. For power, we had a 20 kilowatt diesel generator and the huts were heated with diesel stoves. During this early part of the year, when temperatures are still between minus 15 and minus 35 degrees Celsius, these stoves burned about a 200-liter drum of fuel a week. By the time this fuel is delivered to the North Pole, it costs about $5 a liter or $20 a gallon in 2008 currency. The occupants of each hut collected the fuel from the runway where the C-124 in several flights had delivered a depot of 800 drums. When the drums were empty, we chiseled out one end and used them for garbage, cans, and for human waste. Just like everywhere, an important ingredient of the quality of life is water. Floating on it, as we did, is not much help because the salt water from the ocean corrodes the plumbing and leaves a salty residue on everything. The fresh water for drinking, cooking, and washing had to come from melting the nearly salt-free ice from old pressure ridges. The ice chunks were carried into our wash house and put in a large electrically heated vat. Everyone who took a shower or washed his clothes was required to replenish the water with chunks of ice. By the 18th of May, the entire team of scientists was on station, and by the 1st of June, the official beginning of the IGY, the entire observational program, was in full operation. Many instruments were deployed, including these to measure the intensity and reflection of solar radiation. Both solar and infrared radiation from clouds and atmospheric water vapor are the largest components of the surface heat budget, controlling its melting and freezing. Another device was housed in this box. It was similar to a tide gauge, and it recorded the vertical motions of the ice due to the loading of the ice by snowfall or the unloading when surface meltwater runs back into the ocean. With this makeshift apparatus, we generated tiny earthquakes in the ice. The propagation of the compressional waves generated in this way are used to study the elastic properties of the ice. In those days, we knew little about practical sea ice problems. related, for instance, to its bearing capacity. This is important to know because it determines how safe it is to land a plane of certain weight and landing speed on sea ice of a certain thickness. Several scientists were engaged in studying this by taking ice cores and measuring the salt and air bubble content, and by subjecting carefully cut and measured plates of ice to fracture tests. Some of these fracture tests were perhaps more accidental than systematic. This scientist has just made a thin section of ice and is taking it to his universal stage that uses polarized light to observe the orientation of the individual crystals. The orientation is also something that affects the mechanical properties. Several other scientists were engaged in measuring ocean currents, the depth of the ocean, the composition of the sediments, and the complex life cycle of phytoplankton and its dependence on nutrients and light. Except in the summer, when pounds of meltwater make the runway unusable, we had a plane land every couple of weeks with supplies and spare parts and mail and fresh food, and also replacement personnel and people with short-term projects. This was, of course, always the big event, even for our two pet husky dogs. Pulling these metal strips under the aircraft engines to catch the drips of dirty oil, tragically, one of our men was hit in the head and killed by the last snap of a propeller. It is a well-known phenomenon that people working under adverse conditions and in great isolations sometimes develop a strong feeling of ownership toward their particular projects, and that the arrival of new or replacement personnel can be perceived as something not entirely welcome. This was particularly true for those of us who were there for the long haul, that is, for the whole geophysical year, rather than for a project of a few days or weeks. Toward the end of October, it starts getting dark at 85 degrees north, and also cold. Of course, not as cold as on the Antarctic continent, but cold enough to slow down everything. More deliberate planning is needed for all outside activities, what tools or spare parts will be needed, and how long it will take. Even at our relatively harmless winter temperatures of -25 to -45 degrees Celsius, bare hands and metal objects are not a good combination. Paradoxically, it is also better not to work up a sweat, because wet thermal underwear loses much of its insulating value. Careful weather observations were taken every 3 hours. They were coded and immediately sent to Alaska by radio to be included in the global weather network. Twice a day, we launched a weather balloon to record wind and temperature up to near the top of the atmosphere. Helium to fill these balloons was too expensive in those days, so we had to use the somewhat more risky hydrogen, which we made on station in a pressure tank filled with aluminum chips and caustic soda. Before the sun goes below the horizon and it gets completely dark, the visitor to the Arctic is treated to a spectacular sunset, lasting for many days. This time-lapse shot shows how the sun spins down almost parallel to the horizon before it stays down for the rest of 2 months or more. On the 27th of April 1958, it finally happened. Several cracks appeared in camp, the first one right next to our laboratory, stretching and breaking the electrical connections between the lab and the instruments out at the observation sites. Then more cracks ran all over the camp, damaging the maintenance shack and other buildings. A wide lead opened, separating us from our airstrip, cutting through the stack of fuel drums and sending many of these precious commodities into the ocean. All this doesn't happen suddenly, but fast enough so that within a few hours it was clear that we were in serious trouble. On the other side of the camp, a large pressure ridge formed near the radio hut and pushed over the antenna tower. You can see how the boulders of broken ice are piling up and how their weight pushes down the ice in front of the advancing ridge. While this was happening, we frantically tried to bulldoze the deep snowdrift around the hut, but the tracks of the bulldozer were too narrow and it got hopelessly stuck and had to be shoveled out. This shot shows the actual speed of advance of a pressure ridge. You can walk away from it, but it will grind up everything in its path. And it is just about to do that with our fuel drums. The noise that this makes is disconcerting, to say the least, and unlike any other, ranging from a deep grumble to high squeaks mixed with occasional pistol shots generated by the cracking ice. Most of the huts had been put on heavy 8x8 timbers that would allow us to drag them over the ice if necessary. This was of course impossible as long as they were half buried in snow. So for a day or two we did nothing but clear the snow around the buildings and cut all the cables, connecting them to each other and to the power generator. And of course, we had to salvage as much as we could, including food, equipment, and lumber. We don't have much footage from these events because every pair of hands was needed, and standing around with a film camera was, shall we say, not socially acceptable while all the other men were breaking their backs.